No more singing Newsies. I'm not doing it anymore.
So you hear one of those type of songs, it just gets stuck in your head.
Mm-hmm.
I have like the one from Les Miserables, like the beating of the drum.
Mm-hmm.
Like I have that one stuck in my head.
All right. So if both population standard deviations are no, and they're both at least 30 or normal, you use the z-test. This is 8.1 right here. If both populations are normal, or the sample size is at least 30, but you don't know, so this is a no on knowing the population standard deviations. So this way you know what sigma is, and on this one, these are both 8.2, and this is using S, a sample statistic rather than a population. So it's a two-sample t-test. So you're going to want to have out your t chart, which is A18 for your book. It's on page A18. We're just yawn crazy today. I was about to be done with yawning, and then I looked at Noah, and Noah was yawning, and I was like, well, here we go. Okay. So this horrific formula down here is in pieces, and I don't know why they don't just put it into a big thing. But when you do your test, your t-test, do you see again how we have x minus mu over sigma, right? But remember that the mu's, that's the control group, so this is 0 right here. So it's really just x bar 1 minus x bar 2 on the top. And on the bottom is this, which is this, which is this. And this part right here is this. So it's just like, why don't you just put it all into one big formula, which I'm about to do. Okay, so here's the big final formula you need. T equals x bar 1 minus x bar 2. I'm not even going to write minus 0. We'll just leave that on top. And on the bottom of the fraction is this horrible, huge square root, which has n1 minus 1 times s squared This is why I was confused that this formula wasn't on your sheet. But I think they're just going to have you do the thing. And then that's multiplied by another square root, which is 1 over n1 plus 1 over n2. So it's like this huge fraction where the top is just, I don't know why I wrote it so far over here, x bar 1 minus x bar 2, and then the bottom is that big mess. And that's if the variances are considered to be equal. So if the variances are equal, you use this formula. If the variances are not equal, you use a much simpler formula, which is t equals x bar 1 minus x bar 2 over the square root of s squared over n1 plus s2 squared over n2.
That's like what we did yesterday.
Yes. But you just use the s's and use a t-chart if the variances are not equal. If the variances are equal, use that horrible formula. Another way that they've described this before is instead of saying variances are equal, they'll call it pooled. As in like, we're going to pool our money, we're going to put these together essentially and weigh them at the same time. And whether or not something is pooled or not equal, they'll say that right in the problem. So it's not like something you have to like sleuth and figure out. You just assume, and if it doesn't say anything, you can assume that they're not equal to each other.
There's gotta be such a cluster putting in a calculator.
Let's find out.
Oh no, it can be done.
All right, so we're going to do it by hand. don't even know if I want to teach you how to do this by hand. We might as well, right?
Yeah.
Yes?
A pen or a pencil I could switch to,
Yeah.
What do you have?
a black marker.
If the math wasn't so dense, I could keep it.
Here, fill this up back there. You want a pen or a pencil?
A pen.
Okay. So, if we go to the second page, it gives you instructions on how to do this. So we're gonna try this together. We're gonna do each one of these by hand, and then we're going to do it in our calculator, so you can see that it gives you the same answer, okay? All right, so verify that sigma 1 and sigma 2 are unknown, that the samples are random and independent, that either populations are normally distributed, or both N1 is greater than or equal to 30 and N2 is greater than or equal to 30. All right, so it says the results, oh, I never copy the results, my bad. So it was like, they're shown at the left. No, they're not. What is this, state mathematics, right? All right, so we'll do it over here. Well, we'll do it on the left because I said it was on the left. All right, so teacher 1 and teacher 2. Teacher 1 has a X bar of 473. That's a test score. And the other teacher has an X bar of 459. The standard deviation of the first teacher is 39.7. And the standard deviation of the second teacher is 24.5. The sample size of the first teacher was 8, and the sample size of the second teacher is 18. Okay, now let's pretend that this was an AP test. Can somebody raise their hand and tell me, compare the two populations for me? Or the two samples?
Teacher 1's students scored higher on average.
Mm-hmm.
Because
Because
they have
they have what?
less.
Oh, you shouldn't say like on an AP test, it's because they have less, but you could say it's a much smaller sample size. So one kid out of this 18 messing this up could really lower this quite a bit compared if you had 8 kids that were doing really well, right? But what does this mean? This teacher 1 has a higher standard deviation than teacher 2.
The students are more inconsistent.
Yeah, so they're very varied, right? So actually teacher 1, it looks like, I mean, look at that spread is almost 40. On average, their spread is 40. That means that you've got a couple brilliant kids in that class and some kids that have some lower scores. And they're, even though they're averaging higher than the other class, they're very diverse. Where this class, they're a little bit more consistent with each other. Okay, so the results of the state mathematics test, random tests taught by 2 different teachers at the same school are shown on the left. Can you conclude there is a difference